Hey Mathemateurs, today's presentation is about long division. First, let's consider what division means. What does it mean when you divide 32 by 4? Well, it's a multiplicative problem because it involves groups. 32 divided by 4 means that we're going to take 32 of something and put them into 4 groups. We could start to solve this problem by distributing these 32 things with 1 in each group. And it doesn't take too long before we're giving out all 32 and dividing them evenly into groups. This is why division is a multiplicative process. It's part of multiplicative reasoning because we have groups that are all the same. 4 groups of 8, a total of 32 stars. If we want to do a long division problem, it means that we're going to have to use substantially larger numbers. We're not going to have simple division like we did with 32 divided by 8, where we're just basically recreating a multiplication or division fact. In this problem, 349 divided by 3, the first way I'm going to do this is to show the sort of standard way that probably all of you learned to do this when you were in school. It begins by asking the question, how many times does 3 go into 3? Now, in our standard algorithm, for some reason which I've never really understood, we ignore the fact that this 3 is 300 and simply ask the question, how many times does 3 go into 3? We say that it goes in 1 time, and we put 1 on the top line, and we subtract 3 from 3 because 1 times 3 equals 3. Again, aside from a series of steps, it's pretty hard to understand why this makes any sense, but we've learned the rule and so we follow it. Next, we bring the 4 down. Of all the things that we do in this standard algorithm, bringing the 4 down makes the least amount of sense, at least to me, but we do it because we're supposed to. Now we ask the question, how many times does 3 go into 4? Again, this is actually 40, but we're going to ignore the fact that it's 40 and just use 4 for now. And so once again, we decide that 3 goes into 4 1 time. We put the 1 on the top, and we subtract 3 from down here, and then we bring that 9 down. Alright, the final step is to say, how many times does 3 go into 19? And we would agree there's 6 times. 6 times 3 is 18. And we have 1 left over. This is the correct answer. It's also a kind of bizarre way to reason your way through this, because if you forget the steps or mix up the steps at any point, you're going to get the wrong answer, and you're not going to know it because this is based on a procedure, not on understanding. Let's consider this problem from a different point of view. Rather than say, here's a series of steps that allow us to solve a long division problem, let's think about this in terms of a number sense strategy. How could I go about solving this problem using what I know about place value and numbers and making groups of things? Well, I could say, let's divide 349 into 3 groups. It doesn't take long to realize this strategy would take me a very long time. I could shorten this process by distributing the numbers in large chunks. I could start by giving 100 to each group. This already takes care of 300 in my 349. Next, I could give each group 10, and that would take care of 30 out of the remaining 49. Finally, I could give 6 to each of the 3 groups, and each group would end up with 116, which is exactly what I got when I used the procedure, except this particular approach makes a lot more sense. In other words, I can reason my way through it. I can use number sense to figure this out, rather than just following a series of steps. This approach to division is called a partitive approach. think of it as putting the whole dividend, which is the 349, breaking it up into parts. So this is called partitive. Another approach to long division is quotative, and this is a technique that I particularly like because it looks a lot like an algorithm and it's pretty easy to implement, and it uses all the same number sense ideas that we use when we use partitive division. I start by asking the question, how many times can I take 3, can I subtract 3 away from 349? Well, I could keep subtracting 3's and just count the 3's that I subtracted until I was all the way down to nothing, or to 1 in this case. But that, just like putting individual stars into piles, that takes a long time. So we have to use what we know about simple multiplication to make this faster. So I'm going to ask the question, how many times can I subtract 3 from 349? I'm going to put this line on the side here so I can keep track. And I'm going to start by using the absolute simplest multiplier I can for subtracting 3 from 349. And I know that if I take 100 3's, 100 groups of 3 out of 349, I am going to be subtracting a total of 300, which is going to leave me 49. Now, how many 3's can I get out of 49? Well, I could use 10 3's, and I know that 10 3's is a really simple multiplication problem. That's going to get rid of 30, and so I'm going to be left with 19. And then I know that 6 3's will get me really close to that. And I'll end up with 1 left over. So the total number of 3's that I took out of or subtracted from 349 was 116. Interestingly, just like the other approach, the partitive approach, I can use any numbers I want here. If I want to take 5 3's away and then 1 3 away, that works just as well. This approach to long division is called the quotative approach. Rather than saying, if I divide 349 into 3 groups, how many will each group have? That's a partitive approach. This is saying, if I subtract 3 from 349, how many times can I subtract it? So if we're dividing 349 by 3 using 2 number sense strategies, we can use a partitive strategy that suggests breaking 349 into 3 equal groups, or we can use a quotative strategy that asks how many times can I take 3 away from 349, and the way we solved was to take 100 3's away, then 10 3's away, then 6 3's away. Please remember that in both cases this only gets us to 348, and we have a remainder of 1 in both cases.